Hello, fellow pedestrians. In this series of mini lectures, we will try to get the hang of O.D.Es up to second order, using from basic to more advanced techniques, avoiding where necessary rigor when possible, and implement those techniques mainly through examples. Well, just like a proper pedestrian would do. The only prerequisite one could ask for in differential equations is knowing your integrals, because every differential equation will always come down to solve an integral, every one and each of them. But of course, this is skippable because you don't really have to force yourself to be able to solve integrals. There are many online calculators or softwares one could use if he really wants to get the grasp of differential equations without have to get to know and be able to solve complex integrals. Um, that being said, I will try to explain some integrals when possible, but we won't be focusing on solving integrals that much. So, to start with, what is an O.D.E? O.D.E stands for ordinary differential equation, right? And we'll explain what every word here is. Ordinary, let's start with differential. Okay, differential means that, let's say, you have the most general O.D.E, which is, let's say, a function of y of order n, y of order n minus 1, etc., and y and x is equal to 0. Now, this is how orders of differential equations are denoted, and this can be written like order of n, meaning that y is a function, of course y is a function of x, x is our independent variable, and there is only one independent variable. This is what ordinary stands for, meaning that you only have one independent variable to solve around. Partial DE stands for partial differential equations, where you have many variables involved. So, for our case, where we only examine O.D.Es, you have a function of y, and it is differentiated n times. This is what that means. So, this is a function of y differentiated n minus 1 times, etc., 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 up to the simple function itself, which is 0. Of course, there could be the variable be multiplied here or everywhere. It doesn't really matter. What we are really going to be concerned about are first order D's and second order D's. Why is that? Because first and second order are the differential equations that are of the most importance in nature itself, in physics, and everything can be written down as first or second order differential equations, like we have Newton's equation or Schrodinger's equation, and many more. And also we have Dirac's equation being first order. Also Klein-Gordon is second differential equation, and many more. And most of them are up to second order. So it's a much more important subject to be able to solve first and second differential equations. And if you stumble across a higher order differential equation, you can always, well, not always, but there are many cases where you can drop down a constant. You can reduce the order of the differential equation. So the reason why this is very deep and profound, and it has to do with Lagrangian formalism and how it is acceptable. I mean, the most experimental theories we have right now are the standard model and coming from the standard model action and Einstein, I think it's called Hilbert, Einstein-Hilbert action, which only include up to second order, and they are most fundamental scientific theories we have up until now, and this is the reason. And you could have a whole new video around it, but let's just say we have acceleration, which is nothing more than the second derivative of position with respect to time. And if you really want to be able to express a system around its terms, then you also need to have acceleration. So both in Newton's law or in Schrödinger's equation, second order differentials are there, and this is really why we will focus at these two. Now, to check how this course is going to unravel, it will involve the following in the exact order. First, we're going to examine first order O.D.Es, starting with separable O.D.Es, which is the simplest form of differential equations, having the form y prime is going to be equal to a function of x times another function of y, and this can be separated and solve this equation. Secondly, we have homogeneous these homogeneous in the sense that you have first derivative of y, and everything can be written as a fraction of y over x, meaning that you have a general function of multiplied x and multiplied y's, and they have the same order, the same degree of homogeneity for both of them, right? Let's take a moment here and really check what homogeneous stands for. Homogeneous in differential equation. Let's say you have a differential equation with many terms, doesn't really matter what, and you may have x here or x squared here, and if this is not zero, this is a homogeneous differential equation. If this, however, depends on some function of x, a non-zero function of x, then this is a non-homogeneous differential equation. And we'll check many kinds of non-homogeneous differential equation as well. But this is what homogeneous and non-homogeneous stands in differential equations in general. This is just an abuse of wording here. Now to continue, third we have the general linear first order D, which does have an exact solution, and it is written as y prime plus a function of x times y is equal to another function of x. This can immediately be seen that is non-homogeneous equation due to this term right here, and it is also linear. What does linear mean? Means that the order of y in each term that is summed is the same. So if we had something like y here or y squared here, this would be linear equation. But it can be proved easily that the first order general linear differential equation has an exact solution, and we will check what that is. Fourth, we have exact differential equations using a method called the integration factor when needed. It's not needed at all times, and it can be written as a function of x and y dx plus a function of x and y dy is equal to 0. Also we have second order. These, well, we will examine differential equations with constant coefficients. Let's say you have a form of a y prime prime plus b y prime plus c y is equal to 0. This is a homogeneous equation, and we will also check how a non-homogeneous equation of this form can be solved based solely on the non-homogeneous term, right? And of course these are all constants. Secondly, we will examine the Euler's, the Euler's differential equation. I was skeptical about this to begin with, but the reason I really want to involve this differential equation, it's not something difficult or anything, but the real reason is that it's something that will come up later on when we are dealing with power series, and when a power series diminishes or is truncated to a polynomial, then we will encounter something called the Euler differential equation, which is of the form x of n. Well, just write the second order, so x squared y prime plus x y prime plus y is equal to 0. This also can be non-homogeneous as well. Third, we have a great range of techniques called scaling and shifting symmetries, or on x and y both, and they can be very useful when we try to reduce a second order differential equation to first order, and use later on techniques that we have already learned to solve first order differential equations. And we can exploit these techniques, both scaling and shifting, when necessary, to be able to do that. And finally, the infamous power series solution, where things are going to become a little more involved, because we need to examine multiple cases. First, we will going to check on singular points and what these are, and how could these points lead to decay and or divergent catastrophe on this power series, or they could just behave nice and be as solutions to our differential equations. We will also check what power series convergence is, and some ways to check if power series converge. And last but not least, we have the Frobenius method, which is a very useful and a great way of dealing with second order differential equations. And when it works, it really works. I mean, it's a very profound way of dealing with second order solutions. And we also check linear independence, because when you have a second order solution, you would expect two linearly independent solutions, whereas in first order you only expect one solution. For the homogeneous part, of course, you will also have one solution, one extra solution for the non-homogeneous part, and here as well you have two linearly independent solutions plus one solution called y of p for the non-homogeneous part. So that pretty much sums up everything that we are going to cover in this mini series regarding first and second order ODEs. Thank you all for watching, and I will see you soon on the first video of this series. Thank you all.